What did we learn from the last 3 videos? We have learned that the axiomatic definitions for both inner products and norms are more general than the simpler definitions that we started with, because the axiomatic definitions work for infinite dimensional vector spaces as well. Now for norm, we can see that not all norms are actually induced by inner products. So there we have 2 types of them, the general norm and those induced by inner product. So those induced by inner products are of course special cases of the general norm, and the ones that are induced by inner product have some additional special property. Now we have been talking about infinite dimensional vector spaces on and off. So let's take a look at some infinite dimensional vector space examples as well as some finite dimensional examples of norms. We start with Rn and we take some number p greater than or equal to 1, does not have to be an integer. Then we define this complicated stuff, and one might show that this will be a norm. This is called the LP norm. If I take p equal to 1, then we get L1 norm, something which I have already seen. And if I take p equal to 2, then I get the L2 norm. This is our usual norm, which is also called the Euclidean norm. Now, proving that this will be a norm for general p is not entirely trivial, especially the triangle inequality part. And then you will have to prove something called Holder's inequality as well as Minkowski inequality. You can look up any standard text in case you are interested in the proof. Now it is interesting to note that out of this huge LP family, only the L2 norm is induced by an inner product. And the inner product is obviously the Euclidean inner product or the usual dot product. And it is not at all difficult to show that the others are not induced by inner product using the parallelogram identity. Now a limiting case of the LP norm is the L infinity norm, which is defined like this. You take the maximum absolute value of its component. It is not very difficult to see why it is called the L infinity norm, because if you start with the P norm and let P go to infinity, you will find that the P norm will basically convert to this. Now this is again another norm, and you can check that this is not induced by any inner product. Next, let's take an example of an infinite dimensional vector space over R. So this is the space of all continuous functions from closed unit interval to R under the usual pointwise operations. Now I am going to define one inner product on this. So I take 2 members of this, that is 2 functions defined on 0, 1, real valued continuous, and the inner product is defined as the integral 0 to 1 fx gx dx. It's integrable because the product is continuous and we are integrating over a closed bounded interval. So that will be an inner product, quite easily checked. Now it will of course induce a norm. That will be square root of the integral of fx squared. Now I can also multiply this with something like x squared. Basically I can multiply it with any positive function and still that will be an inner product. And here also I can define the LP norms. So you take absolute value of f, raise it to the power p, integrate over 0 to 1, and finally take the pth root. That will be the LP norm, and as before, only one norm in this family will be induced by an inner product, and that will be the L2 norm, which will be induced by this inner product. And as usual, you can define the L infinity norm as the maximum absolute value of f over this interval. Okay, so that's basically a taste of various inner products and norms over one infinite dimensional vector space. I shall wind up this video with 2 terms. When I talk about inner product space, you understand that I have a vector space together with an inner product defined on it. Now if I have a vector space and a norm defined on it, which may or may not be induced by an inner product, do I call it a norm space? Well, I do not call it a norm space. We call it a non-linear space. Linear space meaning the same thing as a vector space. Okay, that's it for this video.